Welcome to Coding Adventures. I'm so excited because today is Pi Day. Pi, not as in food, but as in mathematical constant. And also today is the day when I'm gonna start a new coding lesson. We are talking about functions, and at the end, because it's Pi Day, we're gonna end the lesson with a few activities around the pi mathematical constant. We'll see how to calculate pi. Okay, so let's get started. Alright, so I'm here in my code editor, and as you can see, I loaded the program already. I'm not starting from zero. And if you pay close attention to this program, you'll notice that it's one of the very first programs that we built together here on this channel. Is the second program actually, is the program with the bear. So let's see it. What a funny bear. It's kind of cute, but it's not even colored. We didn't get the chance to color it. Nevertheless, we built this program in our very first coding lesson. And as you remember, if you remember since then, we just used only one instruction. Or at least this is how we call the circle when we build that program. We said we're gonna build a program using an instruction called circle. And that worked great for us. We got the concept and we built the program and we have this beautiful bear. But what I didn't tell you back then is that this circle keyword here, this circle, is actually a function. And functions are the subject of the today lesson. So basically, starting now, we'll not call these ones instructions, but we'll actually use the proper name. And these are actually function invocations. So in other words, when we are looking at this program, we can say that in order to build this bear, we use the circle function, which comes with the codeguppy.com environment, which is actually based on the p5.js library as we discussed last time. All right. So see, functions are not difficult. We already used functions until now. So let's end the lesson now, shall we? Not so fast. There are still a few things that we can learn about functions. What about let's make our own instruction, or shall we call it function? I think we should call it function. So what about instead of circle, let's say we want a fancier circle. Let's say we want a double circle, something that, draws two circles. We'll start small in the beginning, and then let's see how we design that kind of new instruction or new function, how we build it, and then more importantly, how we use it in our programs. Okay, so let's start with a new code here. And as we said, we're gonna name our new instruction double circle. And we're gonna name it just like that, in one word. It's very important in JavaScript when we name things not to use two words with spaces, just only single word. And we are using, as you can see here, the camel case convention, which is very popular in the JavaScript world. All right, so let's see how we basically build this double circle instruction. And the way to build it is very simple. Basically, all we have to do, first thing, choose a name. We already picked double circle. Then put function in front of that one. And open and close round parentheses at the end. And below that, place a code block. You remember now code blocks. We used them before with fors, we used them before with ifs. And if you remember, inside the code block between these curly brackets, we can basically place multiple instructions. And in this particular case, this is almost all. So basically, we are intending to define a function that is named double circle. And this is basically, this code block is the body of the function, It's basically where the entire logic of the function sits. So, how can we make this one? Perhaps, well, we can make use of existing instructions. This is the beauty of JavaScript. We can build on existing concepts and gradually build bigger and bigger concepts, right? So since we already have an instruction for circle, why not use that instruction twice, a circle inside a circle, and basically that will be our double circle. Let's try to do that. So perhaps we should place a circle at coordinates 400, 300, radius 300. And as if you remember, our canvas resolution is 800 by 600, so therefore this circle will be straight in the middle of the canvas with the biggest radius we can draw, basically. And let's place another circle at the same coordinates, but perhaps with a smaller radius, like 10 pixels smaller. And let's run the program, shall we? Well, nothing. Shouldn't we expect two circles? Well, indeed, we expect two circles, but the reason the two circles didn't appear is because we didn't use yet this function. So functions, in order to do their effect and basically output results, they need to be called. Imagine the function circle inside the built-in library of the environment here. Until we call it, the function circle just sit there quietly waiting for the user to call it, right? So let's call double circle and see the effect. And the way I'm going to do it, I'm going in front of the function, and to call it, we are just typing in the function name and then parenthesis, parenthesis, exactly like it appears here basically. And then I'm going to put a semicolon. Now, notice here, when I'm calling the function, I'm basically putting a semicolon, but we don't have a semicolon here, right? So this one says function double circle and has a code block immediately after, exactly like with the for, exactly like with the if. We don't have a semicolon here at the end. Don't put that semicolon there, it's not good. But when we are calling individual instructions, we separate them with semicolon, right? And calling it means basically invoking, or we are asking the function to run, to execute. So let's try now the program. Boom, double circles. We have two concentric circles, exactly like we designed it. And if you are wondering, where should we call it? Should we call the function before where it's defined or after? Let's try to move this line after. And we'll run it, and we still see the result. How comes? Actually, this one is easier to understand, but how comes that is running also when it's we are calling it before it's actually defined, since we know that the program executes from top to bottom, and basically all these instructions are executed in order. Well, functions, there's a special case here with these functions. You can basically place the call to the functions even before they are defined. JavaScript environment executes a weird trick. Advanced programmers call it hoisting. But it's just a fancy name of basically saying that the functions are just automatically put by the runtime up to the top, so they are ready to be run. So, but what it means for you is that you should not be concerned of where you place the call. You can place the call before you actually define the function or after you define the function, and you are in good shape. But just do this one when I basically mention it. Don't do the same with the other instructions of the program. You'll just mess it up. Programs at the end of the day execute in order. All right, so we have a double circle, but this program is, or this new instruction is not very useful, as you can see here, right? We would expect basically perhaps to use it similar to how you use circle, like to draw double circles in various positions on the screen. And if we remember circle, basically this one here, we see that we are calling circle similar to this one, but we are passing here some arguments. So why not design our double circle to take the same kind of arguments, to take the coordinates where we want to place the double circle and the radius of this double circle, right? Wouldn't it be nice to say if we want a double circle in the middle of the screen? Well, it is right now in the middle of the screen, but just because we just put these numbers here. But let's say we want a smaller circle, a double circle here. And just to see what I'm saying, let's place a circle, simple circle there. Perhaps a circle at 100, 100 and radius of 50. And let's run it. And we have a small circle here. But can we do the same with double circle and make this big one appear actually instead of the small one here? So in other words, instead of having here circle at these coordinates basically have double circle at these coordinates? Would it be nice? Well, let's try it. So we are putting here some numbers. We are asking the function to draw those coordinates, but the function still draws the big circle. And it's normal. If we look inside the body, we see that the function has these two circle instructions. They have certain numbers here, which basically they are hard-coded values. So there's no way for the function to draw in other place unless we tell it to draw in other place. And the way we do that, we parameterize the double circle function, or in other words, we make it accept arguments or parameters. So let's say this one should accept an x and y coordinates where to should place the circles, and the circle should have radius r. So we are placing here some x, y, r variables, similar to how we place inside the for, but notice we don't place a let or anything of that nature. We just say this function should accept arguments x, y, and r. And then we have to use them inside. So instead of drawing at these coordinates, we're gonna draw at x, at y, and radius r. And the second one we draw at x, y, and radius perhaps r minus 10, the smaller circle. And now notice here, when we are actually invoking the function, we're calling it, we are actually passing the actual values for x, y, and r. So we are invoking double circle at these coordinates. So when we run, x, y, and r will take these values. So the body of the function should do a proper job this time. Let's see it. And it does indeed. Let's draw one more double circle just to test it, to be sure that we didn't mess up anything. Always test your program whenever you have the chance. Okay? So let's draw another one. Perhaps this time we should place it in the middle of the screen and radius 200. And it's working fine. We have two double circles. Let's make them closer. Maybe the second one should be at 5 pixels distance from the big one. Right. We have two nice double circles. Aren't these nice? Well, let's save our program here. Let's name it double circle. And save it. And as always, I'm placing the link to this program on the chat, just in case if you want to open it on your side. Although, try to always type it in yourself. It's very important to type in code. Learning to code requires a lot of practice. And after you do a certain practice, you just go beyond the point where you can just write code like you're playing the piano. Well, yeah, unless you don't know how to play the piano, and then this one doesn't apply. But you got the point. So what if now, look what I'm gonna do. I'm going in this program and I'm gonna copy this function into the clipboard and keep it there for a second. I'm going back to the home page and picking up the bare program that we had it before, right? We have this one since lesson 1. And now I'm placing the function somewhere at the end. Pasting. You know, I copied this one from the other program. And you know, if I'll just run it, it runs the same. But what if I'm going right now in this program and replacing circle with double circle each time it appears? Let's see what happens. All right, I think we are done. Let's run it. We have a double bear. Let's call this one double bear. It's still not colored, but well, that's for another lesson, or as a homework to you. If you are inclined to pick nice colors, maybe you should color this bear. So we have a double bear program right now, and let me check it. Oops. I override my original bear. Oh, that's so bad. Always use save a copy if you want to just save it under a different name. but fortunately it's very easy just to revert to the original one. Just replace double circle with circle and you should have the original bear back. All right. So, and all this was possible by defining a function, and we made the function accept some arguments, and then we use this function. Okay? Looks pretty easy. Let's try one more time, shall we? Let's pick perhaps let's see if I can find it. What is this one? Yeah, that looks the right program. Yes, it's kind of a big loose program of loose lines of code. What if we should put this one in a nice compact function, perhaps call it car, and if we want to place a car on the screen, we'll just say place a car at these coordinates, and that should work. Because right now, it draws a car on the screen at the coordinates that we specify here via this variable. So let's save a copy. Let's not repeat the mistake. And then we attempt to do here car with functions. And let's just wrap the entire code in a function first. So we're gonna say function car. We open and close curly brackets, and we take the entire code and place it inside function, inside the code block, and then I'm indenting a little bit the code just to see it that is basically belonging to this code block. And if you remember, we are using here on this channel this convention of opening the curly bracket here on the next line after you know, certain entities such as function, ifs, and so on, rather than on the previous line as you know, more advanced developers are doing, because this is a little bit more easy to read, especially at the beginning level. All right, so if we're running this one, should not do anything, because this code right now, by placing it in a function, it just sits there idle, and the program expects us to call it when we need it. It just doesn't fire up whenever it wants. So let's call it, and let's see if we didn't introduce any mistake. We should have the same result, which is the same. And now let's parameterize it. So instead of having this variable x and y here, well, these variables, they should come as arguments. So we should send them from outside into the function and then invoke it. So we place x and y there, and we remove altogether these lines. And now, if we are running it, we need to specify here where to run it. If we'll not, we should get an error. Let's try it without specifying, just to see it. Yeah, well, in this case, we're not seeing anything. In other cases, it may crash with an error. The reason being, x here is using all these calculations, but we're not providing an x. So depending on the case, may not do something, or may fail, may produce an error, an unexpected behavior, the program may go on a different path. Always check what the function expects and call it appropriately. So here, perhaps we should call it with 100 and 100. And if we are running now, we should see the car again. And now, because we have this program, because it's encapsulated in a function, one of the roles of the functions is code reuse. So let's reuse it one more time. Let's place another function, another car, perhaps in the middle of the screen. Boom, we have two cars. This is fun. Let's have one more car. What about 500 and 200? Boom, another car. Not 100. These are so close. 150. This is so fun. With functions, you already see the possibilities. We don't have to repeat the same code. Once the function is written, perhaps somebody writes this function for us. We are working on a project together with a friend. A friend is in charge of building a really nice function to draw a nice car with lots of colors, you know, with lots of details. We don't know exactly, and we don't care how the function is built. Perhaps we don't even see it. Our friend is, like I put it down below in the program, our friend is just telling us how to use it. It gives us the source code of the function, or in certain cases, even the source code can be obfuscated or hidden, but let's say it gives us the source code of the functions, but we are not caring in seeing how it's implemented. We just use it. Our friend is saying, use this one passing this argument. And when we are running, we can see the program runs fine without knowing how that car is designed. And this is cool because it enables multiple people to work on a project and split different responsibilities. They split this program into smaller modules. In other ways, functions enable us to modularize programs. This is basically a major benefit of function. Just imagine a big program that is just split in functions, and all these functions call each other and working together just to achieve the big effect. All right. So yeah, like I mentioned, code are good for modularizing a program. So let's take another program and modularizing a little bit. This is cool. I like it. Let me share it with you as well. Car with functions. Boom. The link is on the chat. Let me pick another program. One of our previously written program. Perhaps the one with the car. From the beginning, when we draw the car with lots of shapes and colors. Let's see if this is the one. Right. This is the one. And let's save a copy. And this one will be again car with functions, car drawing with functions. Functions. I had a typo there. And let me get rid of the balloon because it looks nicer without the balloon, right? So let's modularize the program a little bit. Perhaps we can have a function to draw the car body, another one to draw the wheels, to draw the ground, the sun, and so on and so forth, and they'll call each other and we'll have a beautiful program at the end. So let's start with the sun here. So we can have a function, call it sun, and we'll take all this code and place it inside. Like that. And perhaps we should place the comment above the function. Now, if I run it, I should not see the sun, which is correct because we are not calling it the sun yet. So that is correct. Let's do the same here. Let's say function ground, which is basically the background there. And we put the code. And if we run it, our ground should disappear again. Yes, the car is in midair. Now, what we can do, we can place these loose lines of code in a single function, name it perhaps car, and we can have then car, ground, and sun, or we can even modularize it even more, which is possible. So let's do that, just for fun, for exercise. It's not necessary since this is such a tiny program, but for our understanding and working with functions, it's important. So let's have one wheels, which basically should draw the wheels of the car. And this one should be function car body. That should draw the car body. All right. And notice none of these functions, they take arguments. And the reason being is because this is just a static drawing and we can parameterize it if we want, but like we did before, but it's not necessary. The main point here is to just use function to modularize a little bit the program. So if I run it, everything should disappear. We just have this empty background instruction, which we can also get rid of it if we place it in one of the functions. So we can now start calling the functions one by one, but I want to do before one more thing. I don't want to call car body and wheels at the same level with ground and sun, right? I want to have a function car that actually calls these two other functions. So when I'm using the function car, it's all I need to draw the car. So I can have a function car, and the function car will call inside these two other functions, car body and wheels. All right, looks okay. So with this being said, our program can look like this. We can call car. We don't call it all car body and wheels because once we're calling the car will quickly call the other two, but we're gonna call ground and sun. So let's call it here, ground and sun. All right, and let's keep this close together because this one is at the same level with this one. So what's following after this? They are just functions or implementation details, how advanced programmers like to call this. So let's run it. Boom! And we have the same drawing. And you know, it's interesting because we can build now maybe libraries to call like that of different backgrounds, different cars, and we can combine them. We can call them a different car on a different background. We can add sun or we can add clouds. We can combine this really quickly once we build these helper functions that help us draw various elements on the screen. All right, so this list looks really cool and also worth sharing with you. Let me put it here in the chat. Car drawing, sorry, I have a spelling mistake. Drawing with functions. See, functions are not that difficult. They are very, very easy to understand and use. And perhaps we should just right now switch to our notebook and let's understand a little bit, a few more details about functions, shall we? So I'm gonna switch to this one. And basically, let me tell you that there are 3 types of functions that basically we're gonna explore today. And 2 types we already saw them. But before even doing that, let's understand into what we built here. And basically what we built here, we built the programs, or we built programs. Let's say this is our program. And inside our program, we just use functions like circle. This is what we did until now, until the past, right? Also, inside our program, we defined new functions, which are these blocks here. We defined the functions car, we defined the function sun, right? And our program was calling into these functions. And not to mention that car was calling into other functions inside the program, like into the function car body and so on. But there is a whole world beyond our program. And actually beyond our program, there are libraries full of functions. So just imagine here that our program sits on a bed of libraries. So some libraries, let me represent them to these rectangles. And these libraries sit on top of each other, in a sense. So here they are, perhaps I should say, yeah, maybe let me place another one at the bottom. In this one here, let's start with this one on top. So these are some built-in functions, like the circle function. Let me put it here really quickly. So circle function sits in a library here that it's included with our program. And circle function actually doesn't know how to draw the function, the circle itself is actually calling in other functions that are sitting in this library. This library, let's call it, this is P5.js. Actually, it's a pretty popular library, and you'll see that in one of the advanced lessons, actually, we migrate from codeguppy.com environment to P5.js sketches on bare metal. So this library that sits on top of P5.js implements circle. There are also other useful functions here. We have also other libraries in here. P5.js is a pretty big library here. Let's say this library, this one perhaps, is named P5 Play. These are real names actually, right? This one actually, it's a small game engine. Yay! Which contains many functions. And if you remember from the second lesson, the function sprite, that one is coming from this engine. This one is also sitting on P5.js library. In other words, when we are calling, for instance, from one of our functions, we are calling into sprite, we are actually calling in this library, the sprite function, and sprite function is calling into other functions inside the P5.js library. And if necessary, this one may call into other library, perhaps into, let's say these are the JavaScript built-in functions. Built-in functions, and we'll get the chance to learn more about this one. But as you can see, starting from the top to the bottom, our program that we are actually writing is just this small part here, actually sits in this box, right? So we get the chance to write some loose code, and then we get the chance to define some functions like these ones, and all these ones will call into a series of other functions found in libraries. And I'm gonna show you how to basically browse this library and see what's inside. What else besides circle do we have here? Do we have a rectangle here? Yes, it is in this library. Do we have the ability to draw a sprite? Yes, it's in this library. And knowing what we have at our disposal, we can create really beautiful program calling into those functions. So there are two aspects: knowing about what functions exist to know how to call them, and the other aspect is how can we define our own functions or our own instructions. And is this basically what we learned today? All right. So this is our program again. Let me just switch again and look one more time at the program before I'm switching back to the paper. So we have our program built with functions. All right, so I'm gonna now switch on the paper and basically see three types of functions. And today, like I mentioned, we're gonna just look at three types of functions, basically at these simple type of functions that they don't take any sort of arguments. And they are useful just for grouping a series of instructions. Second, we're gonna look at the other type of functions that we saw before, like, where was the double bear? Yes, in here. Functions that basically take arguments to do the effect. And then we have another type of functions, and I'm gonna mention about it in a second. All right, so with this with this being said, let's switch back to the notebook here. And I'm always encouraging you to take notes. It's very important. Even if you have an electronic notebook, just use a paper-based notebook. So let's let me put here the three type of functions. So I'm gonna split it in three equal columns, or not that equal. So the first type here, it's a simple one. We just say function. We put a function name, fn, open and close parentheses, and then we put a code block. All right. The syntax, again, is very important to remember. The syntax is this one. Write the keyword function, pick any name you want for the function with the same reserved keywords like we discussed for variables. They don't put here numbers or funny names. You can name a function named function or functionlet or something like that. Don't use a keyword. Use English names or whatever other names you prefer. And then, very important, open and close parentheses here. And then inside the curly brackets, which follow the function definition, you can put as many instructions as you want. All right. So remember this syntax and write it as is. The only change that we do here, you just pick your function name. The rest, don't touch it. Write it as is. The second type of functions is the one with parameters, and we write it function. And I now realize I should have made the column bigger. Let's name this one fn again, just to have space. And here you can put arguments. And you can put as many arguments as you want, separated them by comma. So this is what you customize. In this case is the name plus these variables. Again, separate them by comma. And it's also important, of course, inside just to use the X and Y. They become available to you to use inside. All right, so how do we call the first function? We'll call it very simple, saying fn, open, close parentheses. Since there are no arguments inside, you don't put anything here, but it's still mandatory. It is still mandatory to open and close parentheses, even if the function doesn't take any arguments. All right, if you don't open and close parentheses, everything will fail. All right, so by looking at this one, if somebody shows you you don't see anything in a program, but you see some statement that looks like this, some name, and then open and close parentheses. Just by looking at it, you should know that it's a function invocation. Basically, you are trying to call the function called fn. All right, so this one, how do you call it? Again, you put its name, you open and close parentheses, and then you actually passing inside these parentheses the values that you want to go in x and y. Perhaps you want to put some numbers here like that. And at execution time, these numbers will go inside x and y here, right? So you specify it, and you can call the function again, and you can put a different numbers. It's all fine. Just pay attention how many arguments the function has here. You should basically pass the same. There are some advanced techniques to pass different types of arguments or different number of arguments, but those are, let's leave those for other time. And now there is the third type of functions, and I'm gonna just switch back into the code in a second here, because we saw the function actually, I think on Friday or on Thursday last week. So let me locate perhaps the one with the prime numbers. Let me locate this one, it's prime number. And yes, this one is a good one. And notice here, sqrt. And when we discuss about sqrt, we even said sqrt, it's a function inside the library. So we are just calling it. But this function, it's a little bit special. It doesn't draw any circles. It doesn't draw any lines, doesn't prompt any message box to appear on the screen. It just returns a number, right? And this is the right way to say this function returns a number. And in this particular case, the function receives as an argument a number and returns the square root of that number, right? So it's a function that returns a value. And this is the third type of function that we're gonna mention today, a function that returns a value. Let's put it on the paper. All right, so this one is function. We call it again fn. Can take as many arguments as before. sqrt took just one argument, but can take as many arguments. And just to show you that, I'm gonna use the same arguments x and y here, and then there is a code block here. Now, for this function to return a value, we actually have to use inside a special keyword called return, and here we return the value. Just like that. Return space value, where value is whatever we want to return, right? So, and of course we can make use as before, we can make use of x and y inside, you know, we do our calculation, and at the end of the day we return something that we are interested. So how do we are calling this function? Again, this function, when you are invoking it, when you are defining it, just change here and change the number of obviously the arguments there, and of course you'll have to place this line somewhere inside the body of the functions, inside between curly brackets. So how do you call it? Well, the same as the other ones. So let's call it, perhaps we should call it fn with 100 and 200. Just like that. But then why go to the length of putting this keyword if the invocation is the same? Well, because this function returning it a value, we can capture that one in a variable. So we can say let perhaps v from value equal. And now what is happening, we're gonna invoke this function, and the result, the return of this function will go in variable v. Right? Well, sounds complicated, but actually remember we used already this function last time. We used 3 functions actually, not 1 but 3. We used sign, we used sqrt, and I think we used also random. All right, so we invoke sign, we pass here an angle, and sign return the sinus of that angle or sine of that angle. Sqrt, we paste here a number, and it basically returns the square root of the number. And random just return a number between 0 and 1 at random. We didn't pass any arguments to this one because the function just decided by itself one number to return. That's why it's called a random function. So we just need her help or its help to return a number. All right. So perhaps we did some exercises in this stream with the functions without arguments, function with arguments. Let's try to do an exercise and create a function that basically takes some arguments and also returns a value. And I'm thinking of the following one. All right. I'm also drawing on the, on the paper. Today I'm drawing a lot. I don't know if you like that or if you prefer to write code, but let's see how it turn. So I'm drawing here. I'm attempting to draw a small canvas. You know, our canvas, for the people new to the stream, it's basically an 800 by 600 resolution canvas. It's a graphical canvas, and we have certain instructions, or actually call them functions, that allow us to draw on this canvas. All right, so this is our canvas here. So, and we say we can place, you know, circles, lines. Let's place 2 points here. Perhaps we should place a point here and another point here. And we have an instruction to place a point. But these points, we don't even place them. These are virtual points. We are interested in something else today. We are interested to create a function. I'm going to write it here down, called distance. And these functions will take the following arguments: x1, y1, which are actually the coordinates of this point, and the other point has x2, y2. So we'll take the coordinates, oh, comma again, this is comma, x2, y2. So we'll take 4 arguments, which are basically these 4 numbers, the coordinates of 2 points. Any 2 points on the canvas, can be these ones, can be in any other position. And we are interested in this function to basically return the distance in pixels between the points. So looks like an interesting exercise. Just to give you an example, if we are picking this point here and this point here, since, okay, this canvas has resolution 800 by 600, so we are picking the first point on horizontal and the last point on horizontal, this function should return 800. If we are picking these two, should be 600. But what about if we are picking 2 random points on the canvas, like these ones? How can we find out the distance between them? Well, it's very easy with a little bit of math. So this is more a math problem than it's a coding problem, but nevertheless, we can have fun coding it in the code. So this point has x1 and y1. So what does it mean it has x1? So basically here somewhere we have x1 on this x-axis. Here we have x2. Here we have y1. Here we have y2, right? So if we just do like that, we'll just have these coordinates there. And the way we're gonna find the distance, using some very simple math from the elementary school. Let's suppose this one, it's a square rectangle. And it's actually, it is a square rectangle. So if we go x2 till the end, it doesn't matter. Here we should have a 90-degree angle, right? And right now we know the following about this one. Well, we know this distance for sure, because this distance is x2 minus x1. Or actually it's the absolute value, I should say technically, because we can have the points reversed, but it doesn't matter. And this one, it's actually y2 minus y1, right? So which results, this one, so let's name this one, it's d1 perhaps, and this one is d2. And this one is square root of d1 plus d2. Just like that. So with this information, we are now ready to build our function. So let's get out of this program and let's start quickly a blank piece of code, a blank page of code. And let's build our function here. We're gonna name it distance. That will take x1, x2, y1, the coordinates of the first point, and then x2, y2, the coordinates of the second point. And we are supposed to return, to basically do this formula inside, right? So let's take it step by step. Let's say d1 equal, and we are looking again, d1 it's x2 minus x1. We can have it also as modulo, but it's not necessary since, oh, this one, sorry about that. This one it's square. Oh, that was a big mistake. Our formula would have returned total different result. So let's have that one as being x2 minus x1 square. Actually not square, let's have it just like that. And let's have the other one as being y2 minus y1. Basically this part here. And now we're gonna have square root of d1 square plus d2 square. And this will be the result, right? So, let's take it in a separate variable. Let d, perhaps the variable should be d. The other one is d1, d2, this one is d. So it's basically d1 times d2, times d1, sorry, that will be d1 square plus d2 times d2 square. And actually with extracting square root using the sqrt function, the one that we used last time. And at this point, we always have to say return d. Remember, as we put on the paper, we say return d. So what this tells us, in the moment we're gonna invoke the function, so basically we're gonna invoke it saying let, let's say answer equal distance between point at 100, 100 and point at 400, 300. So 2 points arbitrary on the canvas, and then we can print ln answer. Let's see what will be the result. And we run it, and should be 360 pixel plus something. There is a rounding error here because of the square root and all these numbers. I wonder if this answer is correct. Well, we can double check our math, or there is another way. Actually, we just did this exercise in a redundant way because there is already a function, a built-in function that calculates this, and it's called dist. You know, like distance, but dist. So let's invoke that one and see the two answers, compare them one by one. So I'm gonna just say answer 2, same numbers, I'm using dist and print answer 2. So let's run it. Well, they're the same. Distance, it's our function, dist is the built-in function. And from now on, just if you know, because we have a dist function, you don't have to build your own function to calculate. But let's keep this one. So this one calculates. So this is a function. Let's emphasize the word function. Function to calculate the distance between 2 points on the canvas. And again, this is basically the same as the dist function that is built in. So perhaps somewhere deep in those libraries, if you remember those squares that I put here in the notebook, somewhere there is a function called dist. So into one of these squares where you have circles and the other ones, it's a function called dist that does that, exactly this one. So basically this is a function. This is an example of a function that returns, takes arguments, as you can see here, and also returns a value. And because takes arguments, we invoke it like that. And because returns a value, we can take the result in a separate function. All right. Let's play a little bit more with this one, just to a few other examples. And let me see what we can do here. Oh, always I intend to share these programs with you. So let me share this one with you. So this one is distance I'm gonna save it. I was about to not to save it and lose this beautiful function. That would be a shame. Distance function. It's on the chat. And I'm thinking to open again. I thought about this one. Is prime number. Right. This is a good one. So let me save a copy. So let me name it here prime times. So it's a new copy. And what I want to do is actually create a function that takes as an argument a number and returns true or false if that number is prime. So instead of doing all this work all the time, if we'll have this function in our toolbox, each time we want to check if a number is prime, we'll just invoke the function, all right? So basically what we have to do is, let me clean it up a little bit. We're gonna place, this is the main body of the function. Actually, we're including this one. So let's place this one in a function named is prime. Yep, is prime. And I'm gonna place this one inside. And now, because the function is named is prime, I don't want to name the same variable, to use the same variable with the same name. There are some rules where in some cases this is allowed, in other not. But just to avoid the confusion and because we want to be just in the beginning, have just simple rules, let's rename the variable. Let's name it b is prime from Boolean, to indicate also that this is a Boolean variable, b is prime, and we'll just use it here. All right, but we are not done. Since this is a function that takes a number, perhaps takes n inside, so we pass n as an argument that we're using inside, and once it determines that it's prime, and it does that in this variable, at the end of the fork, that variable contains the answer, we have to return it. So we'll just say return b is prime. And now, let me also remove this one. Like that, we have just pure function here, no invocation. I'm running it, nothing happened. So let's do some tests. So let's say first one, answer 1 is prime 17. Let's see, println, and we can say 17, or let's put here, yeah, for now we can write here just the answer, A1. So let's run it, and says true. True means 17 is prime. Let's try it with other numbers. 16, it's false, of course, 16 is not prime. Let's try it in edge case, 2. True is, it's also prime. Let's try it with another edge case, 1 here. Says 1 is prime, but we know that prime number start at 2. We can adjust our function. So what we can do, we can say here, if n is less than 2, remember the if statement, we take a decision, we look at the number, is less than 2, and what we can do here, we can just say return false. Notice there are 2 returns inside the function this time, but it's fine, you can have as many as you want. The code is executing from top, and it will go inside, and I always said, even if we have a single instruction, it's good practice to place it inside the code block. So basically, if n is less than 2, we'll go in here and say return false. In the moment the return keyword is encountered, the function stops, just stops there. So basically this one doesn't matter anymore. It's like break, but more powerful break. This time we are exiting from a function, and you can exit it even if we put here break, after break put return, just go straight out. So let's try it. 1 is not prime. And now we can test basically with whatever numbers less than 2, and we should hit this code block because of the if decision here. All right. So apparently our function is working properly. And let's try it with several numbers at the same time. Since it's a function, we can basically reuse it and invoke it multiple times. And I also want to show you that a function, because, well, you can just use it, a function invocation that returns a value, you can use it inside an expression. So you don't have to take the result in a variable. You can use it in place of a variable. So instead of A1 here, I can take this entire thing and place it here. So it says is prime 3, print ln is prime 3, and it's true. It's working just fine. So let's duplicate this code a couple of times. Let's try with 2, with 3, oops, with 4, with 5, perhaps with 6, 7, 8, 9, 10, 11. 5, 6, 7. Let me place a couple of values. And then you may wonder why I'm doing this. And soon we should just fix it. Oh, but we don't see the number. But anyway, let's say this is 2, 3, 4 is not, 5 it is, 6 is not, 7 it is, and 11 it's also again. So also to see the numbers, we can just put it here like that and will work. But you know, that's not necessary right now. So we just modified our programs about primed, and we modularized it, and we encapsulated all that logic that deal with how to determine if a number is prime. We encapsulate it in a function, in this function over here. I can even collapse it. The editor has this cool function to collapse it. I don't want to look at it. It's too complicated as of now. I'm just interested in using it. And as I said, perhaps somebody else is building this function for me. Perhaps we're working in a joint team and a more math inclined person will build some cool math functions that we can use. And you know, it's just working fine. So let's extend a little bit this program. Since see, just copying and pasting code like that is not a good idea. Let's invoke this function in a loop and actually find all the prime numbers less than a certain value. Shall we? This should be very simple. So outside of the function, we can have a for, and we take a number. We start at 0, although 0 should not matter because anyway prime numbers start at 2. But let's say you start at 0 just for fun. And we go less than 100, I++. And here we say if. And again, we are doing the same trick. We are just calling the function inside if, like an expression. Instead of putting the variable, we can say if is prime this number. If it is, let's print it. Just like that. That's it. Let's run it. So what should we expect? In the moment we run the program, we should see a list of prime numbers. Let me save it first and run it. And if I'm not mistaken, these are prime numbers less than 100 because that's how we looked. So let's look really closely. And that was fast. Computer is really fast to generate prime numbers. Let's go one more step up to 1000. Boom. Look, the list of prime numbers less than 1000. We have plenty of numbers here. All these are prime numbers. Let's verify one randomly. 929. Let's Google it. Is prime number. Let's say yes. Our program must do something good, which it is. Let's also extract this one in a function. Perhaps function print primes. And let's say this one takes an argument because we want to call it, let's say we want just 10 primes or 100 primes or so on and so forth. And we can also modify it to start at 2. There is no reason to check if 0 is prime, 1 is prime. We know they are primes. So let's take this entire function block, that loose code, place it here, ident it once. And now our program contains just 2 functions. We'll not do anything until we invoke it. So we'll invoke just the first one. We'll put 100 here. There is no need to invoke the second one in our program here because the first one is invoking that one. So just like that. And if we run it, we see the list of prime numbers less than what? Oops. We did a mistake. Instead of, we didn't use n inside function. Our function is still going to 1000. So let's go up to n here. And basically it's doing the right job right now. So we can put some nice comments here. Print prime numbers less than n. And this one, determine if a number is prime. And this is a basic algorithm. It's pretty, you know, it's kind of okay for now. There are more advanced algorithms to generate prime numbers. Prime numbers are so useful in computing. Uh, but even with the knowledge up to this lesson, we are able already to generate prime numbers and play with this one and see how many prime numbers you can generate. You'll see that after a while, you'll have some computer will get a little bit slow. But nevertheless, it's still pretty fast for a reasonable number. So let me share this one with you as well. So maybe this one is printing primes, right? Printing primes, not just primes. I'm copying again the link and put it in the chat. Printing primes. And the program is on the chat. All right, so we saw how easy it is basically to we already knew from lesson 1 how to call functions. Now we saw how easy it is to define functions that take no arguments, take arguments, and take arguments and return values. The 3 types of functions that I just mentioned that we're gonna discuss today, and we use these functions in a few of the programs here. Now let's move into the second part here and discuss a little bit about scope of variables, right? And what that means, scope of variables. Let's start with a blank program just to use it as a playground, experimentation playground. So if you remember from one of the earlier lessons about variables, we said you can define a variable and assign a value, and if you need another variable, just define it like that. But don't define 2 variables with the same name. You know, the program will basically say, no, it's not working right. You'll not be able to run it. Or in some cases you run it, but you expect different results. So don't declare 2 variables with the same name. Yes, of course, it's all right to reassign a variable, but don't define a variable with the same name. So this looks like a pretty big limitation because we saw, for instance, we use I a lot. The variable I. We use it. We said for I a lot, and I said it's a pretty common variable. So I'm wondering, when you are looking in those libraries into how our program is calling into the library with the circle and P5.js, and I'm wondering, nobody else used their I since it's so popular. So how come I could use I? And there is a very good explanation for that actually. You can redeclare variables as long as they are protected. They are in case some some bubbles. So let me show you what I mean by that. Remember the code block? Well, see, I cannot declare I twice, but do you remember the code block, the curly brackets? Look, I don't have any warning here on the side. So let me place here a println I, and let me go in this code block and just put the println I. 100 and 200. Work as expected, but also have a code block like in the middle of my program here. This is not very, well, although it's accepted, it's not also very popular to do programs like that. Instead of a code block, you actually place an entire function, but nevertheless, code block that you encounter it with instructions such as if, with for, also with the body of the function they all have code blocks. These code blocks behaves like bubbles. So where did we encounter until now code blocks? Well, today we encounter a loose code block here in the middle of our program, but it's not very common like we mentioned. But we encountered it before in a situation like with for, when we said for let I equal 0, I less than 10, I plus plus. We encountered it in this situation. That was a code block here. And we encounter it today in a function, fn. That fn is the name of the function, and we encounter it again here. And with the ifs as well. But anyway, with this one are pretty important. So, by looking at this one, we already see that we can basically, the variables that are encapsulated in a code block live inside that code block. We say that their scope is at the level of the block, for instance. And we'll have the same concept at the level of the function and then at the level of the entire program. So let's start with a more complex program here. But before that, maybe, yeah, let's start with a small program here. Perhaps I should define a variable here. And these are just synthetic tests. They are not funny, but still they are important, right? So let's have a variable here, name or number. let's name it n, and we have it n. Let's have a function that we call it, what should we call this function? Test. It has no special meaning, right? So let's have here a println n, like that. And inside the function, we have another n that is 200. And then we println n. And let's invoke the function here. And after we invoke it, we call again println. All right. Yeah, that's what I want to do. But just to see what I'm doing is basically here. So I'm saying here, first print here. I'm saying this print is inside function, and this one is second print. Let's name it like that. So second print outside function. So yeah, so we have a variable n and we are displaying it. Then we are calling a function that sets n to 200. We are displaying inside the function immediately after the n, and then once we finish with the invocation, we just printing n again. So let's see what it does, right? Let's run it. We'll see 100, 200, 100. So notice what happened. We saw 100, inside was 200, inside here was 200. So let me put them on the side. We saw 100 here displayed. Then from inside, we basically saw 200, and then we saw 100 here. And this is quite good and interesting. So what is happening is this variable n, first of all, we were able to declare it with the same name as here, because it's in this bubble. Not only that we could declare it with the same name, but it lives inside the bubble. It lives inside this block. And whatever value it has here, basically this one is not available outside. So our n on the outside is not affected. In other words, here we just declare it and we basically use it. It's 200. We can use it 200 inside, and when we go outside, our n is still 100. It's not impacted by the variable inside, right? By the declaration inside. So the scope of the variables, first of all, they are at the level of the block, and then function, and then at the level of the code. And you'll understand in a second what I'm saying. Let's also place a for loop here. And we can say for n equal, should we say n equal to 1, n less than 10, n plus plus. And let's place, I printed too many values here. So let's run it. And let me put more here. Let me put 5. 0 to 5. Actually, it doesn't matter. So I'm running it. Note, and actually, let's look after it goes inside the function, right? We'll see this println, which is this one, is this n. We have another n defined, this time at the level of the for block and not at the level of the function. So what we should see when it goes inside the function, we should see basically 5 numbers printed, which is 0, 1, 2, 3, 4. And then we should see n, which is this n that is inside the function, not in this one in the code block. The one in the code block, once the code block finishes, that bubble is sealed. You don't see it. So basically, we see this number, and of course, looking at the program from top, we should see basically 100. Then goes inside the function. We should see the 5 numbers. Then we should see 200, and then goes outside, and we should see 100 here again. So here from inside, we expect to see 0 to 5, and then 200 basically. This is what we should expect to see inside the function. So let's run it. We should see 100, then the 5 numbers, 200, 100. See? So, talking again about the scope. Scope of variables, first of all, it's at the level of the code block, then it's at the level of the function, and then these are global variables. And what this mean, the scope, also is that that variable, not only that it remains inside the block, but a block can see variables from its parents up to the global level. So the parent of this code block is the function, and the parent of the function is the global scope here. So let's do one modification to the program. What if we don't have a let here and we just have n equal 200? Let's see what happens. Notice 100 first time is displayed correctly. Inside the function is 200, but once it goes outside, it's 200. And the reason being is that because we are not redeclaring it again, and because this function can access the level of the parent, we are overwriting n this time. All right, so we are overwriting the n value here. And this is good, and sometimes it's good and sometimes it's not good, but just for you to know that it's possible. And if you don't intend to override the parent variable, always put a declaration in front of it. Now, there is also the opposite. In the moment we put a declaration here, from inside the function, I cannot access the global n here. If I want to use a formula here and say n plus 100 or plus 2, well, the n that I'm using is this one, is not this one. So if I want to use the global one, just make sure you don't redeclare it again, and then inside I'm gonna use the global one. So in other words, and let me draw quickly on the here. I think I talked a lot of bubbled around, and maybe some of these things don't make sense. So let me draw again here a program. So let's see, this is our program. And we have some variables here. Let x, let y. And here we have another function. We have a function, whatever name we'll have. And then we have another function. First of all, functions, as we said, they behave like these blocks where variables are encapsulated inside. So basically, inside the function here, we can redefine x and y. Here we can redefine x and y. And this x and y will be just local variable inside the functions here. You'll use them as is, they'll not impact these ones. If you put, of course, a let in front of them. If you don't put a let in front of them, you can have access always. An inner block has access to the parent level, so to the to upper scope. So at any point from here, we can refer an x and y. Of course, I'm saying again, if you don't redeclare them, right? So we can define that as well. And there is another level here, which is a code block. So this function perhaps has a for code block. So this is code block. And the code block is inside the function. And the function is basically inside the, let's say, program. I'm saying here program or global scope. All right. So it's like we have this hierarchy here. So whatever variable sits in the code block, it just sits in the code block here. No, the function doesn't see it, the program doesn't see it, but the code block can see the variable coming from the parent function or can see the variables coming from the global scope, as long as you don't override them inside one of the other levels. All right, so perhaps we should do a little bit more exercises, because this is or rather than do exercises, let's also look at look at some examples that we did until now. Let me locate here let me locate here this one, quadratic equation, if you remember it. And notice here, we have A, B, and C variables. And the A, B, and C variables, let's say they are global. Now, they are available in our program. For instance, they are available in this code block here because they are from the parent. They are coming from the parent. And even if we'll take the entire code, this one, and place it in a function, we'll still have access to those, right? So perhaps we should do that one just to show you. So let me save a copy. Quadratic equation var playing. So let's run it as is. All right. Equation has two real roots, and we did this exercise when we learned about if and conditionals. So this is working fine. And as we say, let's place this one inside a single function. Function equation, perhaps we should name it. And I'm gonna just take it as is and ident it a little bit. So I have it inside an equation. If I run it right now, it's not working because we saw before we have to call the function. So let's call the function. And you'll be a little bit surprised, but the function still runs. And it's a little bit different. We didn't even pass arguments to the equation. So we want to calculate the equation for what numbers, like we did with the circle. We place the coordinates here. We place, okay, I want for these particular numbers, or here, I want for these particular numbers. We didn't even place these numbers here, but the equation still runs. So how come? Well, because from within the function, all variables declared in a global scope are available. So basically all these loose variables that we place on top in the global scope, we say these are available within the functions. And this is good, but also leads to some bad practice. Don't rely on this one, because if you rely on this one, and if you have two functions and one function changes A, the other functions will find a different A there. So you'll have a side effect. Global variables are still good if you know their meaning. Perhaps you want to keep here the score, and you know that that variable keeps the score, and all the functions that will access that variable from the global scope should just read it, and that's the score. Perhaps you could put you should just read it, and just this single function at the end of the game should update it. All the rest should read it and display it on the screen. So global variables are good, but don't use them. Use them as less as possible. Each time you need to pass to use variables inside functions, if you want to pass data from outside, like we're passing here this data from outside, make sure your function is parametrized. So perhaps this function should take ABC as arguments, and then you will be able to invoke it like that with arguments. And if we run it right now, we should have the same result, but now the function is reusable. First of all, it doesn't make use of those variables, and I can even use it, invoke it twice, perhaps here with different numbers. And if I run it, this is the complex of this. This is the first invocation. This is the second invocation. So this particular set of numbers made the program go on a different branch. All right. So quite of a lengthy explanation, but remember this hierarchy of three things. You have block. Actually several blocks inside the function and several functions inside the global scope of program, and variables are visible at the lower block level, and then but each of these lower level blocks, they see the variables from above. One from the for instance, this one from the if, it sees A that is coming from above, basically this time from the parameters, but all could have been defined here, let A. So blocks see the functions and see the globals don't see inside. Also, block provides this isolation, which allows you to redefine the same variable several times. All right, so this is, I'm gonna share with you this new we can still even further continue with this one, because we can split it in several functions and so on, but it's getting late and we want to do another exercise, perhaps equation with vars. I placed the program on the chat there. All right, so now now perhaps because it's pi day and we just talk and talk and talk and we didn't even mention about the pi. What is pi? It's not some food. It's just a mathematical constant. So and you probably know pi, it's 3.14. Let's see how we can calculate pi in our program. So let me quickly go here on Google, and I want to search an article on Wikipedia by Bellard. Bellard is a talented programmer that basically came up with this formula to calculate pi. It's an interesting formula, and he says here that it's 43% faster than the other formula. Let's see the other formula, which was this one. Actually, you know what? Let's calculate pi with this formula because it's shorter and we can do it maybe a little bit faster. So how can we put this formula inside the code? And of course, this is maybe you consider it a useless exercise. Everybody knows pi is 3.14, and even this environment has a constant named pi. We used it last time, that just basically gives us that number. But perhaps we don't know the pi and we want to calculate it. So let's do this exercise. Let's do this one in code really quickly. So we're gonna start a new program here. And look again. So this is a sum of this expression, and this expression is summed from 0 to infinity. Obviously we cannot go to infinity, that would be impossible even on the fastest computer, but we can go to a big number, maybe 100, 200, and see how this sum will look like if it starts to approximate pi. Pi is an irrational number, so obviously you'll have to go to infinity to basically reach all the decimals, but we're gonna just limit it ourselves to, you know, some intermediate number. So let's try to write this expression. I'm gonna put this one on the left here just to have it a little bit clear. Okay, so it's just above my head over there. So let's write a function here, calculate pi. And this function will have to do a sum of some expression. So let's calculate first this, let's extract and do a function to calculate just this expression, and then we'll sum them. So we'll have a function, let's have a function, calc expression, and expression takes basically is based on k. We'll use k as argument here. So we'll just, well, we can have it like that. Well, let's use several variables just to make it a little bit simple. So we'll have this in a variable, this in a variable, this in a one, this in a one, and this one in another one. So let's start with the first one. Let value 1, it's 1 over 16 to the power k. Actually, we have a function, and now we can use the terminology called pow, that we with 16 and k as arguments, and actually we'll raise 16 to the power k. And we'll return that value, and we are using this one in an expression, so we can say over 1 over 16 to the power k. That's first value. Let's take the second value here, this one, which is 4 over, and we'll put in a parenthesis, 8 times k plus 1. All right, the other one, the v3 there, it's 2 over 8 times k plus 4, semicolon. The v4 equal 1, this one 1 over 8 times k plus 5, and the last one equal 1 over 8 times k plus 6. Whew, lots of typing. I hope I put them right. So now we have to return, and will be v1, which is the first part here, multiplied with, and inside the parentheses we'll put v2 minus v3 minus v4 minus v5. I think I got them right. v1 and inside the parenthesis v2 minus v3 minus v4 minus v5. I think I got them right. So this is an expression, and what we can do, we can test it right away just to make sure that we didn't introduce an error here. So before we finish everything, we can calculate an expression for 0, perhaps for 1 and 2, something like that. We print 3 numbers, and oops. This one is not printing, it's just returning a number, so we have to print it. Print ln of this one. So let me quickly wrap it in println like that, and if I run it, I should see, well, as you can see, the first one returned 3 point something, so probably when these numbers will get up, they'll converge towards 3.14, which is pi. So let's see. Looks okay. So let's do this sum here. So calculate pi, maybe should take as an argument an n. We cannot go to infinity, so we'll calculate pi up to 100 iterations. So we're gonna do like last time, the algorithm for summing, we're gonna use like we used last time, so refer to the previous lesson. We'll start with a sum initialized with 0, and then we'll say for let k, and we can use k again here, it's fine, we are in another function, we don't, this k is totally isolated inside this function, sits there, is not interfering with this one, so we can use this one, is 0, k less than n, again we are going up to n, not infinity. It would be bad to go to infinity, our computer will freeze and crashes and we'll have to reset it. So we are adding to the sum, well, we are adding to the sum this expression actually, so we are invoking this function. And I'm using here, I could have taken it in a variable, I could have said value is calc expression like that, and sum then is plus v, but I can also use directly in an expression, since it's a function that returns a value. And we are passing as an argument k. Now notice, we are passing the actual k here, the 0, the 1, the 2. That one will arrive inside this function, and will be used here and return a value. Alright, so looks okay, but this function needs to return something. Needs to return the final sum. And now we have two functions, they don't print anything, we have to, let's take in a variable here. Pi value equal, I'm just saying pi value because we have, there is not pi, there is an uppercase pi defined, but let's say pi value. Calc pi, and since we are running on a computer, we can make it calculate 100 of these expressions, and then let's print. Let's see the result. Ta-da-da-da-dum. Ta-da-da-da-dum. We have pi on the pi day calculated with this formula by Bailey, Borwin, Plouffe. I think I didn't say it correctly, but well, that was quite interesting. We calculated our own pi value. Let me name this one calc pi. You know what? Let me name it calc pi 1 because I want to do one more. I know there are different kind of formulas, so let's do one more. So let me place this one on the chat. Calc pi 1. It's on the chat. Let me Google for another formula. Let's see what other formulas are out there. Let me calculating pi. All right. Okay, this one looks cool. Let's choose this one. This one looked exactly like the one on that page before. Let's go back to the other page, this one. There are different ways of calculating pi. This one looked like that one in the picture. 4 over 1 minus 4 over 3. Yeah, I think we can calculate this sum. Well, let me open the other article because the formula was expressed much cleanly there. It says pi over 4 equal this series. All right. Can we calculate this one? I hope so. So is this one over here? Oh, there's another formula. Okay, but we're gonna use this one, Gregory Leibniz series, which says here that it's well-known and beautiful way. Well, we like well-known and beautiful ways of calculating pi. So how do we approach this one? We see here that basically it goes 3, 5, 7, 9. We notice how that series goes. So perhaps we can make a function called pi again. And obviously here we'll have to do minus plus minus plus. So we'll have some sort of a initial value 1 from which we subtract, add. Yeah, so we can have a initial value. It's not really a sum, but I'm still naming it a sum. Is this 1? And then we subtract 1 over 3, we add 1 over 5, we subtract 1 over 7, we add 1 over 9, and so on and so forth. So let's do a for loop, and we'll use an I variable that starts at 3, perhaps. We subtract 3. And this one, they repeat. So the next one is with 4. The step is 4, basically, what I'm saying. So I less than, perhaps we should also place here an n. We go up to a certain value, and then I plus equal 4. So we go to the next part here where the series starts to repeat. So from the sum, we subtract, this time minus equal, 1 over I, which should be 1 over 3 initially. And then to the sum, we add 1 over I plus 2, which should be 5. When the loop repeats, I is 7. I think we are right. I'm not sure exactly, but let's hope we are right. So this one will calculate the entire thing, but in order to return pi, we need to do 4 times that thing, because this is 4 over pi. So basically we are returning 4 times sum. Let's see if we did it right. If not, we'll abandon the program. Let pi value again. Let's say calculate pi. Let's choose an arbitrary value for n to go up to 100. This series sometimes converge for big numbers. So let's see. ln pi value, and let's run it. Moment of suspense. Well, I think it's still a success. It's not 3.14, but we are getting closer to pi. Let's try to go up to 1000. It starts to converge. So apparently this, let's go 10,000. This is a very big number, by the way. When we put here 10,000, we'll have a very big for loop. We'll cycle through a lot of numbers basically to go to 10,000, but let's see. Yeah, 3.14. We got already the third decimal, should be 5, this one. So let's go more, maybe 100,000. No, we still get 6. I should be 5 here. Let's go to 1 million here. Not only that we got the 5, but I think after 5 comes 9. So we got pi with pretty good precision. But, well, the difference is that this series converges much slower than the other one. But nevertheless, we calculated pi again. And it was a nice exercise, not only to create a function, but also to remember how to use for loops in here. So calculate pi 2. And yeah, I can share this one with you. Or you know what, from now on, these 2 last exercises, I'm gonna let you type by yourself just to practice. And I'm thinking to do one more pi exercise this time, really quickly. Okay, so grab me my notebook. I'm thinking of something graphical this time. It's not a very practical method by any means, but I'm thinking the following things. I'm thinking of a canvas. Let me switch here. I'm thinking of our canvas, but before that, let's place a circle here. And I'm gonna place it in this corner here. And we know the area of a circle, it's pi r square, right? So if we'll have a way to measure the area, and of course we'll know the radius because we draw the circle of a certain radius, and if we have a way to measure the area, then pi is area over r square. So we can find basically the pi by measuring the area. Imagine that you are on a field and you need to know pi, and well, the way you'll do it, you have some small tiles and you start placing tiles in a circle as closely as possible, but you form a circle, and then you know that each tile perhaps is a 1 square foot and or something like that, and then you count the tiles, then you determine the area, you measure with a ruler the radius, and you divide them and you figure out the pi. It's kind of a pointless exercise, but still gives us a little bit of chance to play with coding nevertheless. So the way I'm thinking to approach this one is to basically imagine that we have a circle here and we don't even have to draw it. I'm just using the left corner because the coordinates is 0, 0 here, and it will be a little bit much easier to do the math. And this circle, let's say, has radius of r. So if it has radius of r, has an arbitrary radius of r, right? So we should have r here, we should have 2r here. We are putting the circle inside the tight square, so 2r here. So what it means to basically measure the area. Imagine that this one, of course, we are not on a field and we don't have tiles, but inside this circle, these are made of tiny, tiny pixels. So we are actually counting how many pixels are inside the circle. And by counting how many pixels are inside the circles, and I drew the pixel a little bit bigger here, it's basically, we know the area in pixel square, if you want. So if we know the area of the circle in pixel square, we can divide it by radius square and we figure out the pi. So how can we count the pixels inside a circle? Well, what we're gonna do, use a nested for loop to scan the entire rectangle, the entire square. It's actually a square. This guy here, the one that contains the circle, it's actually a square. So we're gonna use basically a nested for with an x and y to loop through all the pixels inside the square. And we saw last time that it's very easy to loop rows and columns with a nested for, so we're gonna use the same approach. And we loop through all the pixels, but the question is, and then for each pixel, we're gonna measure the distance from the center to that pixel. And the center is actually at coordinates RR here. So this is the center, it's the coordinates RR. Since we are choosing the radius R and we're placing this in the top left corner at 0, 0, the center is radius R. So what we are doing, we are calculating the distance between an arbitrary pixel at coordinates X, Y, and the center at RR. So what we're gonna do? Well, if the distance is less or equal to R, if it's less or equal to R, then what it means? It means that it's inside circle. Because all the pixels inside the circle, perhaps we should pick a pixel somewhere here. See? The distance from center to this particular pixel is less than radius. And the maximum distance is when it's actually on the circle itself, and then that distance will be the radius. Any pixel from outside, for instance from here, well, for sure the distance will be bigger than radius. So therefore we are going again on this for loop, and we're gonna loop and loop, loop in loop, and then for each pixel we calculate the distance, and now we have a formula for the distance. We just did it before, or you can use the built-in one. And then if those pixels, we determine that they are inside the circle, we add them to the area. Once we calculate the area, we divide it by r square and we should get our pi. So let's get started. We have a little bit of work to do. So we'll not, perhaps we should start with a function, calculate pi, and basically, yeah, so basically this, let's say, a circle, we start with a circle of radius r, right? that we want to use as a measure. And what we're gonna do, we'll have two for loops for let x equal 0, x less than 2 times r. Remember that we're putting in a square of 2r radius, x plus plus. And we go for the other one, for the vertical as well. Also, we go down to 2r, y plus plus. And at this point here, we are iterating through all these pixels in this 2 by r square. Let's figure out the distance between x, y, and the center. So the center should be at r coordinates. And what we can do, we can make a decision here, saying if the distance is less or equal than r, then means it's inside the circle, so we increase the area. So perhaps we should have a variable here, let area. So yeah, let area. Initially it's 0. We assume the area is 0, but once we encounter pixels that are at this distance, we can basically increase the area. So we can say if the distance is less or equal than r, area plus plus. We increase area once, right? So area, boom, boom. Like we encounter one new tile. We counted when we place those tiles on the field, we counted one more tile. So we encounter one more tile. So here, after we finish the looping, area should contain an arbitrary number, or the area of the circle. So if we want to calculate pi, because this function is called calculate area, calculate pi, not calculate area, we should just return area divided by, let me look to my notes again. Yes, and they were r square here. So divided by r square. I'm gonna just use it like that. So let's see the result here. So let's take in a variable, calculate pi for a circle maybe with a radius 300, and we print the value. Let's see the result. Very close to pi, actually with 3 decimals here. Now, of course, in order to increase this one, you need to have basically a bigger circle, and you'll converge closer and closer to pi. So this one is calculate pi version 3. Just before we close this exercise, let's also visualize these pixels. Let's put a pixel with using the point instruction. By the way, this didn't happen on a canvas. It's on a virtual model of the canvas in our memory, inside computer memory, somewhere virtually. This didn't use any drawing instruction on the actual canvas. We didn't use circle, we didn't use point, we didn't use any instruction. All these distances were calculated virtually, like we assume there is a canvas, we assume there are points, but all these were just pure mathematical calculations in this program. But now we're going to use a point at x and y coordinates and actually plot the points on the actual canvas. Let's see what we look through. Actually, if we place all this, will be a rectangle, I guess. Yeah, it's a rectangle because we plotted all the points. But if we place this instruction inside the if, and again here I didn't follow the advice, even if you have only one single instruction, place it in a block, because if you want to add the second one, we need to make sure it goes in the block. So here, if the distance is less than r, we are increasing the area, so must be inside circle. So let's put a point there, and we have a circle. See? So all these points that we plotted right now, we also counted towards that area. So we counted all these points here, and that is our area, and we divided that by r squared, and basically that gave us the answer to pi. I'm commenting this line since these points are so many, the program becomes slower than without it. So right now it's a little bit faster, much faster as a matter of fact. All right, so with this, I'm ending today's lesson. I hope you had fun, even though we went a little bit into too much theory with the scope of variables. I think will require a little bit more practice, and there is that much that we can say in a lesson, but we'll continue doing more and more exercises, and basically this will make sense. I also realized that we are going at a higher speed with the lessons here. So I fully recommend you to do lots of practice. And even if you don't practice, continue watching the series, because by doing more exercises and watching more, some things will be better clarified in the future. Okay, so thank you for watching. Happy coding, and see you next time.